Good morning, everyone. My name is Krishna Dubey, and today I will be presenting a presentation on visualizing vector field. And I am currently pursuing my BTech degree in CSE from Acropolis Institute of Technology and Research. Moving ahead, we have the presentation goals. The primary goal of this presentation is to build a clear understanding of what vector fields are and how they are can be visualized. We will explore various techniques used in both 2D and 3D spaces, understand their application in real-world scenarios like fluid flow and magnetic flow, and examine the tools used for effective rendering. And this session will also address common challenges and will look at recent advancement in this field. What are the learning objectives? By the end of this presentation, you should be able to define vector fields and their components clearly. You will learn how to choose appropriate visualization methods such as streamlines or arrow plots and interpret what these visuals represent. You will also gain an insight into how these concepts are applied in the engineering, physics, medical fields, and visual effects. Importance of vector field visualization. Vector field visualization is essential because it simplifies the understanding of complex directional data, whether you are simulating airflow over an aircraft wing or analyzing water currents. Visualizing vector allows you to guess patterns that are otherwise hidden in raw data. These visuals are not just to clarify, they are vital in decision making, design validation, and scientific discovery. What is a vector field? A vector field is a mathematical function that assigns a vector to every point in space. Each vector has a direction and a magnitude. This makes it ideal for describing physical forces like wind, gravity, electrical fields. In computer graphics, the fields are visualized to study the flow or forces at every position in a given space. Scalar fields versus vector fields. Scalar fields provide only a magnitude at every point, like temperature or pressure. In contrast, vector fields give both magnitude and direction, making them more complex and informative. Understanding this distinct is important because the visualization techniques used for scalar and vector fields differ significantly. Components of a vector field. A vector field consists of three main components: the position in space where the vector is defined, the direction in point is, and its magnitude or strength. These components collectively determine how a force behave at different points and allow us to model complex physical systems visually. Vector field representation. Vector fields are typically represented using arrows, also called glimpses, that points in the direction of the vector whose size indicates magnitude. These visual elements are plotted on a grid or a surface to make the invisible force or movements visible and interpretable by a human eye. Basic visualization techniques. These are several ways to visualize vector fields, each serving different purposes. Arrow plots or curve plots give a snapshot of vectors on a grid. Streamlines illustrate continuous flow patterns. Path lines trace the movement of an individual particle, while streak lines show the trajectory of particles over time through a fixed point. Arrow plots. Arrow plots are among the most basic and widely used techniques for visualizing vector fields. In these plots, arrows are drawn over specific points, and their direction and length represent the direction and magnitude of the vector at those points. They are particularly used for steady fields and where the data flow does not change over time and are easy to interpret even for beginners. Streamlines. Streamlines are smooth curves that follows the direction of the vector field at every point. They are especially useful for visualizing the flow of fluids or air, as they give a clear, continuous picture of how they behave over space. Each streamlines is tangent to the vector field, making them ideal for studying the overall flow pattern in a static field. Path lines and streak lines. Path lines and streak lines are techniques used in time-dependent vector fields. A path line shows the trajectory that a single particle follows over time, while a streak line visualizes the path of all the particles that passes through a specific point. These methods are vital in understanding dynamic systems such as fluid dynamics and particle flows. Color coding in vector fields. Color is a powerful tool for enhancing vector fields visualization. By assigning a color based on the magnitude or another variable, viewers can quickly understand the intensity of the field. For example, hotter colors like red or orange may indicate higher magnitudes, while cooler colors like blue suggest lower values. This added layer of information makes complex field easier to read and analyze. 2D versus 3D visualization. Vector fields can be visualized in both 2D and 3D depending on the nature of data. 2D visualization are simpler and faster, often used for teaching and simple analysis. 3D visualization offer a more realistic and a detailed representation but require advanced tools and a computational power. Choosing between 2D and 3D depends on the application and the complexity of the data. Glimpse-based techniques. Glimpses are small shapes such as arrows, cones, or disks, used to represent vectors at different points in space. They rotate and scale based on a vector directions and a magnitude, providing an intuitive and a compact representation. These techniques works well on both structured and unstructured grids and is commonly used in engineering simulations. Texture-based techniques. Texture-based method like line integral convolution (LIC) enhances vector field visualization by applying textures along the direction of flow. These methods are particularly effective for dense vector fields where drawing individual arrows or streamlines would clutter the view. The result is smooth, continuous representation that reveals subtle pattern in the data. Volume rendering for vector fields. In complex 3D environments, volume rendering provides an advanced way to visualize vector field. It allows us to see what's happening inside a volume, not just on the surface. By rendering semi-transparent flows and combining scalar data like pressure or temperature. These techniques are widely used in medical imaging, fluid simulations, and scientific research. Application in physics and engineering. Vector field visualization is a core tool in physics and engineering. It helps simulate and analyze airflow over structures, electromagnetic field behavior, heat transfer, and more. These visualization guide engineers in designing patterns, better systems, and solving real-world problems with precision. Application in computer graphics. In computer graphics, vector fields are used to animate realistic phenomena like fire, smoke, water, and a cloth movement. Game engines and animation softwares use them to create dynamic environments and effects. They also help in designing crowd motion and particle effects in visual storytelling. Application in medical fields. Medical professionals use vector field visualization to understand and analyze internal body functions. For example, blood flow through arteries or a neural signal transmission can be studied using MRI-based vector fields. These insights assist in diagnosis, treatment planning, and medical research without incisive procedure. Challenges in vector field visualization. Despite their usefulness, visualizing vectors field presents several challenges. Making high density data can lead to visual clutter, making it hard to read. Choosing the right technique for a particular type of data is critical. Additionally, rendering large fields in a real time requires a high computational efficiency and optimized software tools. Solution and future directions. To address these challenges, researchers and developers are working on adaptive sampling methods, hybrid visualization techniques, and a real-time GPU accelerated rendering. Artificial intelligence is also being explored to enhance interpretation and automate the selection of appropriate visualization methods. The future promises more interactive, accurate, and accessible tools. Summary: vector field visualization helps represent data involving direction and magnitudes. Techniques like arrow plots, streamlines, and a volume rendering provide a different perspective depending on the application, from engineering and physics to medicine and graphics. These visualizations are crucial in analyzing and understanding complex systems with ongoing technologies and advancements, and their use will only expand. Thank you for exploring the world of vector field visualization. This topic brings together mathematics, art, and a technology to reveal the unseen forces that shapes our world. If you have any questions, thoughts, or application in mind, now is the time to share and discuss them. Thank you.